All right, guys, this section of today is going over manipulating equations. The first part of today, anybody listening to this, we went over what to do on the lab. Ideally, you can read that lab and get all those instructions, but if you have any questions, please talk to somebody that was here today, or as well as myself, and we can make sure you understand a little bit more clearly. All right, so manipulating equations. I mentioned this earlier, but not on the video, so let's say it again. The purpose of today and starting into tomorrow is to make sure you understand the lab process. Where did my marker thing go? Didn't put it there. I didn't put it there. It's not here anymore. It's in my pockets. I'll find it later. All right. There it is. Okay. Point being, if I give you an equation that you don't fully understand, I want you to at least be able to know, all right, if Spanauer is correct, this is what it should look like. Okay? We're going to focus today on just 1 and 2. Over the course of the year, we'll follow everything else. But we're going to today talk about, let's say you're given the equation of a relationship. What should that shape and its constants be? That's all we're focusing on today. This is maybe a new way to look at this, but this should hopefully be mechanically a review. You understand this pretty well already with a couple things that I want to make sure and cover. So let's say, for example, I give you, I'm going to make up every equation today except for one. Let's say I give you the equation, let's see, cool, let's go yellow surf. G equals L squared. What does this mean is happening in a lab? Well, since there's only 2 variables here, I am changing these 2 variables. I'm changing one. Sorry, I shouldn't say I'm changing. There are 2 variables. I'm changing one. The other one is being measured. Now, if I just give you this and I ask you what it should look like, there is no way to answer that until I follow it up with, I want to know this graph. We mentioned this a second ago, but let's say it again. If I give you that order, what does that tell you about the variables? Either way to say that, by the way. When you there's not a bad word by saying y and x. Y and x is fine. We know what they are. I'll probably say the other one just to make sure we hear both. But yeah, that says y versus x. Now you'll remember, I'm not going to go over it again because we already did these notes. You'll remember that we talked about 4 shapes. You might have those notes available if necessary, but know that the 4 shapes, linear, parabolic, hyperbolic, and square root, all come within very particular equations. And you'll note that all of those equations start with y by itself to the first power. Now you'll notice that since I did it like this, there's my y, it's by itself, it's to the first power. So what I then expect you to be able to do is go over here and just simply sketch. You don't even need to use a ruler or anything here. Label where everything goes and then tell me what should the shape of that graph be. This is not hard. I should have like 5 answers right now. Come on. Not a square root function. What's that? Parabolic, yes. Parabolic, why? Because L is to the square right over here. Questions or concerns? Easiest thing ever. Hopefully we're no questions, but let's move on. But keep in mind, the exact same equation, G equals L squared, does not have to look like that. It's not the equation that looks like this over here. It is that relationship, G versus L. Because if I say the same thing and I say, hey, here's the equation again, but I want to know L versus G. Okay? Quickly sketch, put the answer down. It'll take you 2 seconds. I'm sure this will be the easiest thing ever, but let's make sure we're on the same page because it's not going to be easy moving forward in your notes. And you probably didn't do this because it was so easy, but technically, mathematically, what should we do first? In order to know what the shape is, we want these equations to look, basically mimic the equations of those shapes. And what is true of every single shape? The linear, the parabolic, the hyperbolic, and the square root, what do we do first? We get the y by itself. We isolate the y. So that's what I was looking for. Mathematically, what do we do to this equation? We isolate the L to the first power, basic algebraic stuff. We square root both sides, and we get L equals the square root of G. Correct. Correct. This is a square root function. So, great stuff. Moving forward, super easy so far, yes? Let's move on. Let's say we step it up a notch. Of course. 2 seconds. I have my notes. Stupid way I put them online. unless you want to see it, I don't care. Let's start off with G equals x squared times r minus FPL. This is really where we're at. Now, as you look up there, you will see 6 variables, which is very indicative of something that could potentially happen in real life, where there are 6 things that potentially affect each other. But this next part is important. In a lab, we already said this, how many of these will we actually have as variables? 2. What do we do with everything else? We keep them the same, we keep them constant. Meaning, as you look at this equation, mathematically there are 6 variables, but in the lab there are only 2. Meaning, even though it is a variable, it is going to be held constant and therefore is a constant. Does that kind of make sense? Okay, I'll try to back that up here in just a second. So let's say we look at this relationship. What is G versus R? Begin real quickly in your group. Sketch what that shape should be. Should hopefully take you no time. Hopefully it's easy. If it's not easy or it doesn't take you a lot of time, check with your group just to show everybody what you got. Everybody's so easy. This is just fine, unless it isn't, which is also okay. We'll sketch it. Again, I cannot tell you how important it is. I appreciate people that are vocal about their lack of knowledge. I know the truth of this. I've taught this for 15 years, which tells me tendencies. Not the truth about you individually, but it tells me the truth about all of you. And that is, maybe 2 of you, this will be the easiest thing ever, but all of you have something to learn here. So put down your answer, figure out whether or not it's easy or not moving forward. What's the shape? What is it? No. Linear. Why is it linear? Yes.
Because it's in the format of y.
Correct. Well, you look at the y-intercept is to the first right over here. I didn't make you do any algebra in this particular case. And then you look at the independent variable or the x, and you notice that it's to what power? First. Correct. Right over here, which tells you. Now, what does that mean I did in the lab with everything else, including the x squared? I held it constant. So let's pretend for a second and say I held it at a value of 2. No units on this because we're making this up. So x is 2, but we squared that 2, and it's actually a total of 4. But is that 4 going to change in the entire lab? Which means even though it says x squared here, this whole thing is a constant. Yes? Now if you struggle with this next part, what you do, once you figured out the shape, is lay out the generic equation for that shape underneath. And notice that I've identified the dependent, I've identified the independent. So the next piece of this puzzle is I expect you to be able to tell me what the shape is with y and x labeled, but then I also expect you to tell me what both constants are. How do I figure out the constants? It's real simple. You look at this generic shape and use that as representation. K is whatever's multiplied next to it. So in this case, what's multiplied next to it is x squared. And the y-intercept, or b, should be whatever is added next to it. So what should the b constant be? Negative FPL. And again, it feels weird to put 3 variables in a constant. But don't forget, you're only changing g and r, which means f and p and l are some number that is not going to change. If f was 1/2 and p was 2 and l was 3, the 1/2 and the 2 cancel it out, and 3, that means that this thing is -3. And should that -3 change the entire lab? Not if they're constants, it should stay exactly the same. All right, let's move on with this, okay? Let's try the same thing again, but let's go, no, we are going to shift it a little bit. Let's talk about an equation that ideally you did, that is a real equation, to give you a rough idea of how this works in the lab. Hopefully your chemistry teacher talked to you about this last year. If not, it's really no big deal, other than the fact I'm a little bit irritated at her. I'll probably talk to her sometime when I'm in Edwardsville, potentially. Probably never again. Moving on. So, point is, this is the ideal gas law, which explains to us basic understandings of the way a gas works. But you kind of know this already. If I had a balloon sitting in front of you right now, and I decided it's a particular size. It's a particular size because the pressure in the atmosphere, we'll get into that. Let's talk about the stuff that you should know. I press inward on the balloon. Assuming it doesn't pop, what do you expect to happen to the balloon? I press inward on the balloon, I increase my press, what should happen to the balloon? Assuming it doesn't pop, what's that? I press inward and it increases in volume? Correct, pressure increases, but I mean, just think of a balloon. I'm standing here in front of you right now. Don't like use logic, just imagine what's gonna happen. If I press inward on the balloon, what should the balloon do? Assuming it doesn't pop, it should get smaller, which means what we said is if pressure goes up, volume should go down. That's it. Now, how could we see this in a lab? Some of you just realized what P versus V equals nRT is, and actually how it's not actually that complicated at all, but we'll get into that in a second. So, P versus V, what do you do? Oh, sorry, no. I just said I was changing pressure. That was dumb of me. Volume as a function of pressure. Well, what I do with this is, there's my Y, so what do I do with my Y? Isolate it by, dividing by P. Super easy math here, I know. And what shape should we expect that graph to make? Yes. Number of moles, not important in this particular case, but yes. And its number of moles, R is the Rydberg constant, which can be a couple of values depending on what you use, and T is temperature with an absolute value for very good reason, but we won't worry about that right now. Okay, what shape does this make? Hyperbolic. Does that hyperbolic shape tell us exactly what we just said? As pressure increases, what happens to your volume? Oh, magic. Anyway, but say you're a chemistry teacher or your physics teacher or whoever puts this equation up in front of you and it's weird and it's strange to you or whatever, what can you do with that? You can at least say what it should be in real life if it's correct. And then hopefully you learn the techniques to go out to a lab and change P and measure V and get this graph and go either, yeah, that is what life says, or no, that is not what life says at all. Quick comments real quick. If you don't get this super fast, it's okay. But see if you can't tell me. Discuss real quickly in your group in 30 seconds. What should the constants of this equation be? Discuss quickly. Yes. Go ahead. Discuss with each other. What should the constants of this graph be? K and B.
For that situation, like, if you gave like a real life situation and like wanted us to tell you what the graph would look like, couldn't you, not for that situation, but think that it's linear? Because like it would just
Yes.
be going down.
Yes. 100%. Especially if you zoom in too far. Look at this. If I zoom in too far, you can start to see, ooh, that looks really linear. So part of it is the context of understanding. Part of it is in a lab. That's why it's ridiculously important in a lab that we spread our data out as far as is reasonably possible. Now, early on in a lab, I do that for you. Like I choose your numbers. Like I'll tell you in the first two labs how I did that, just so you understand, because in future labs, you're gonna have to do this. We were limited in the first lab by 20 centimeters on the constant velocity card due to the fact that I know that every single card drifts, and beyond about 20 centimeters, that drift becomes an effect on the overall results that can change them. As far as the acceleration lab, your max was 160 due to the fact that that's how far the cord went before you start to have some issues with measurement. Moving forward in labs, you want to maximize that out, spread your data out as far as possible, and why I told you early on with graphs, it's ridiculously important that that spot is 0, 0. Because if you're not looking, the greatest change usually on these shapes is somewhere in that first between 0. So if you're not seeing it, you're usually going to think it's linear even if it isn't. All right, constants. What's the K constant here? nRT is correct. What's the Y-intercept? 0. Okay. Hopefully, okay, as I look out there, I'm seeing some of you guys kind of downplaying the significance of this, which is fine. That's your prerogative, your choice. You don't have to trust me. As a matter of fact, I push you to be skeptical. Okay. But as I hopefully show you that your skepticism is misproven and that I do actually want you to do particular techniques for very good reason, maybe start to think about the possibility of trusting me when we go over this stuff and it seems way too simplistic for you, because let's see how you do on these. I've made up 5 equations up here, which the relationship is on the right side. You have about 7 minutes left. See what you can do. All 5. That is 5 different equations on the left and 5 different relationships on the right. We probably won't finish this. Do not even, well, for starters, when you take pictures in this class, please ask. Okay? It's a good habit to get into in this digital age. I will always try to get out of the pictures, and sometimes I have no problems with it, but I also really don't like the direct correlation that is avoided by writing stuff down. So
Would you have to
please write
the
stuff
answer?
down whenever possible, which you have the time and space here to do.
Yeah, I was just taking it just in case I didn't have.
And then we'll do that at the end.
Would you want us to write the graph or like the y-intercept?
What you should be, when the answer to one of these should be a sketch. I should see your y and your x, as well as the shape, and then you should tell me what the constants are. But if any of them up here, I think all of them up here actually are in this camp, need a little bit of algebra, my general work on algebra is show enough work that it's perfect every single time. So for some of you, that's going to be 3 or 4 lines. For others of you, that's going to be 1 line, and I don't care, but I expect perfection every time on your algebra.
Does number 5 say 6, 9, or B9?
B9. While you guys here in person are doing this, I'm going to talk about something real quick online. If you want to come back, just ignore me right now and come back and watch it later, that's fine. Well, it's not a super important thing, but it's kind of helpful. So when it comes to physics, there's 2 different directions on how we pursue our understanding. The one that is most popular is like use logic, understand the equation, and then go to a lab to prove yourself. But in physics, there's another technique that is used all over the place that is particularly important, and that is this. We don't know how this concept works, so we just go to a lab and look and see what a lab says and work our way backwards. There are a ridiculous number of complicated ideas in physics that were founded this way. If you come to Physics 2, obviously not all of you will, but if you come to Physics 2, there are so many different ideas that started like this. We don't know. Let's see what the lab says and work our way backwards. That's kind of what we're trying to get here. Well, what we're going to be doing over the next couple days. This technique is very much the first one. This is what we say it is, what should it be, and then we look in the real life to see. All right, I'm going to go over 1 and 2 right now. If you feel like that was super easy, maybe peek up, make sure you have the right answers. But if you have no idea what you're doing, that's why I want to be able to go over these real quick. You will note that obviously 1 and 2 on the equations are exactly the same. And both of them have f for the y variable. So we do need to do that algebra of adding r squared. So it should just be f, oops, hold on, I wanted to talk about this too. VE plus r squared equals f. Now most of you did not write it like that. Most of you wrote f on the left side because that's what you're used to. You certainly don't have to, and quite frankly, there's certain things where I want to push you outside your comfort zone. This is probably one of them. You should be able to work with this equation even if the y is over on the right side. But let's begin with, I think I said f versus, which one did I do first? What was the first one? I just literally had it up here and then erased it. F versus e, all right, what shape should it make? Linear, because e is to the first power. The k is v, correct, and the y-intercept is r squared. Now, one thing you will note, by the way, that I have been saying regularly is I've been saying the k constant and not saying slope. And that is because the k constant is slope, but only for a linear function. So in this particular example, this graph, the slope would in fact be v. But take the next example where we compare, I think it's f versus r, yes? What shape should this make? Number 2, what's that? Correct, parabola, very good. Okay, what should the k value of this function be? Should be 1, correct? You don't see anything in front, so there's an invisible 1 you can use right there. And what should the y-intercept be? VE. So again, I wanted to highlight the fact that on this right side, the k value is in fact slope because it is a line. On the left side, this k value has other meanings that we'll get into a little bit later, but is not the slope because that is not a line. All right, next, n versus p here. We'll cover this tomorrow.